Yeah, so today we're going to talk about some radical expressions. Okay, so we are done with the rationals. This is radical. It's totally different. So we're going to see what these are, and we're going to learn some rules about them, see how to simplify them. And then we're going to spend the next couple of classes talking more about these. We're going to see how to add, subtract, multiply, and divide radical expressions, and also going to learn how to solve radical equations. So a radical expression simply is anything that involves the radical symbol. Anything that has this in it is called a radical expression. Um, so first, let's define them, and then learn some rules. Okay, so like I said, uh, before we get into the details, let's do a little problem here. So what is this equal to?
3.
3. So this is what we usually call it the square root of 9. The square root of 9 is 3. Okay, in other words, the number that multiplies by itself twice to get 9. It's basically the opposite of this. So we know this. When we square 9 or 3, we get 9. So this is basically just the opposite. Here, we go from 9 back to 3. Okay, from 9 back to 3. So 3 to the second is 9. This is we raise 3 to the second power. But to go back, we take the radical of 9. Okay, so the radical is simply the opposite of raising a number
Sorry,
to
that's
a
a
power.
9 on the radical symbol.
I'm sorry, you're breaking up. Repeat that. I couldn't hear you.
The connection is bad.
Yeah, I believe she has a problem with internet. Okay, so that's all that the radical is. It's the opposite of raising a number to a power. So when you raise 3 to the second power, you get 9. The radical or the root is basically going back to the 3. So a number that raised to a second power is 9. That number is 3. Another one also, another example is, we know that 25 is, the square root or the radical of 25 is, of course,
Oh.
is 5, right? So it's basically the opposite of saying 5 to the second is 25. So we kind of go back and forth between these. So this is what we call, this is a radical expression. This is radical form. And this is exponent form because we have an exponent. Okay, so that's basically what radicals are. We're just going back to the root of the number. Here by default, so again, we say 3 to the second is 9. To go back, we say the radical or the root of 9 is 3. So the root of 9 is 3. And that power here, the power here becomes a little number here that we call the index. We didn't see it before, we just write it this way, but there's actually an invisible 2 there. So we'll call the index. It's basically the power here. So 3 to the second is 9, or radical 9 is 3. So radical 9 index 2 equals 3. Radical 9 index 2 equals 3. So all the radicals must have 3 components. Index, of course, a radical symbol, and some number inside that we call the radicand. Okay, the radicand. So let's summarize that here. So we can have some number.
But now it's good.
Okay. Maybe I'll change my device. I'll just probably use my phone. Professor, you might need to let me in because I'm gonna use a different device. I keep getting kicked out.
Okay, I think we got it back now, right?
Yeah, I'm back now, but I'm gonna put it on my phone, so you might need to let me in.
Okay, all right. Go ahead and log in. Here's the thing. Okay, so like I said, every radical has a radical symbol, a number here, the index, and what we call the radicand. This is the radicand, so index. Even though if you don't see it by default, it's 2. If you don't see it by default, it's 2. If it's different than 2, we have to write it. It might be 3 or 4 or 5, whatever number it might be, we have to write it. The number is called the radicand. And of course, this is a radical symbol. This symbol here.
The index is a what, an N? What is
Yes. And yeah, whatever number here, for example, 2, could be 3, could be anything, depending on the power. Whatever the power and the exponential expression is, that power becomes the index. Let me give you another example. Let's say, so 3 to the second, I mean, not 3 to the second, 2 to the third.
What do you say?
What is 2 to the third?
8.
It will be 8.
That's right, 2 to the third is 8. So this is the exponential expression. How do we turn this? How do you go back to the radical? So to go back from 8 to
3, 2,
be radical of 8, right? What's the index?
3.
That's right, the index, the power becomes the index. Okay, radical 8 would be, radical 8 here, index 3 will be
2.
2 here. And you can go back and forth between these as needed. Again, exponential form, radical form. And that's basically all there is to it. It could be any numbers, let's say some base to a power p equals some value a. That's exponential form. Let's turn this into radical form. What is this equal to in radical form? So we're gonna have a radical first. So what's the index of that radical?
P.
That's right, p. So the power is basically the index. Radical of what equals what?
A.
Radical of a is,
B.
that's right, radical of a is b. Basically going backwards, and the power becomes the index. Okay, so that's basically, again, the main concept of the radicals is just going back from raising a number to a power backwards to the root of the number that was raised to that power.
So I have a question.
Mhm.
If the index is not shown, does it automatically put it to the power of 2?
Exactly, yeah. It's by default 2 if not shown. If it's different than 2, then we explicitly write it. For example, 3, 4, 5, depending on the power, basically. So let's see how to simplify. Basically, when you say, for example, let's go back to a simple example here, 16 and 2. So basically the radical of 16, index 2, you think of it this way. What number multiplies by itself twice to get 16?
4.
4. That number is 4.
4.
And when you do radical of, let's say 8, as we did here, basically you say what number multiplies by itself 3 times to get 8? What's that number that multiplies by itself 3 times to get 8?
2.
2.
2.
That's right. It is 2. You can easily check it. You can say 2 to this power, the index is the power, should be 8. So 2 to the third is 8, just like here. 8 to the third is 8. What about, be careful with this one. The index now is not 2, but 4. And let's say you have 16 here. This is not the square root. This is not the square root. It's not 2. If it's 2, then it's the square root. If it's different, then it's a different index. So again, think of it this way. What number multiplies by itself 4 times to get 16?
2.
Exactly. And to check, you can say 2 to the 4th. If you multiply 2 by itself 4 times, you get 16. Okay, so always pay attention to the index here. It's what tells you exactly what to do. Just like when you say, for example, 5 to the second is different than 5 from to the third, 5 to the fourth, and so on. This is what tells you how many times you multiply the 5. Okay, the power tells you how many times to multiply the 5. Same thing with the index, tells you how many times you need to multiply a number to get that radicand inside. So in general, so we say, so what number multiplies by itself n times, okay? N times to get x. That's basically how you should read it. When you read it this way, it makes more sense. You can find most of these radicals, you will see common ones. Let's do a couple more examples here. What is this equal to?
9. No, it's 3.
No, 9. Try to read it in this form. What number multiplies to
3.
by 3 times 20?
3.
Is 3. How do you check if this is correct?
3 times 3 times 3.
That's right.
Times, yeah.
You take this 3, raise it to this power, and it should be equal to 27. Let's check. 3 times 3 is 9. 9 times 3 is 27. Okay, so it's a simple concept. You can go back and forth. What about this?
$25.
Nope.
Oh yeah.
Would be a number that multiplies by itself 3 times.
Uh-huh.
This slide is. Would be 5.
5.
That's right. You can easily check again. 5. Another common cube is 64. Let's see.
For the 3 and the 27, what is it 9 also a number for that one?
This one here?
Yes.
No, it can only be one answer. It can't be 2. There's only one number that you multiply by itself 3 times to get 27. That number is 3.
Okay.
Do 9, it's not going to work. You can try it. Times 9 times 9. It's going to be much bigger than 27.
It's 4.
That's 4.
This is 4. That's right.
It will be 4.
So we can check again by doing 4 to the third. 4 times 4 times 4 would be 64.
64.
So these are the cubes. And of course, you know the common, and what is this equal, let me see. What is this one equal to? Always try to identify the index first, which is?
7 times 7, it will be 49.
So here, the index is invisible, it's 2.
2.
So that means what number multiplies by itself twice, that's 7. And you're familiar with the common ones. So from 1 to the squares from 1 to 10 should be at least familiar with these. So 2, 3, 4, 5, 6, 7. Okay, so all these. When you square these, you get 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Okay, so if you square, so for this side you square. If you square any of these, you get these, but to go back, what do you use to go back again from this to this? Use a square root. Okay, the square root of 100 is 10, 81 is 9, and so on. So again, when we square the power and the radical of two opposite things. One squares a number, the other one gets back to the root of that number. So this is for the squares. For the cubes, you should be at least familiar with the first few. So we have, let's say 2, 1, 2, 3. at least these. What is the cube of 1?
1.
That's right, 1
1.
cubed, and 2 cubed is
8.
8, and
27.
7,
64.
and
125.
125. So here,
125.
that's right. Here, from here to here, we cube. To go back, we get the cubic root. Here, this is the square root. This is called the cubic root. So basically, you go back. So the index must be 3 here. So when you go back from these, you go back to those. Okay, so at least get familiar with these so you can do the math faster without a calculator. Most of the time, it's going to be around these. You're probably not going to see much of the other indexes, but if you see them, you know how to deal with them. And then again, just read them this way. For example, the 4 here shouldn't be hard to find a number, and you can also use a calculator to figure out a number in case you don't see it. Some of them can't always be simplified. For example, we know that the square root of 9 we know is 3, but square root of 8 might not be a whole number or an integer. This does exist, but it's a decimal. I believe it's 2.6 or something, or 7. Okay, so not all the roots are perfect. So if it's not perfect like this, we can possibly simplify it a little more. We will still gonna have the radical there somewhere, or a decimal, but we prefer not to have decimals. I'm gonna try to see how to simplify this without getting a decimal. There's gonna be a root still there. We're just gonna make this number a little smaller and move something outside. And we're gonna get to that in a minute when we see how to simplify radicals. So not every radical equals a whole number here or an integer. Sometimes it could be a decimal, or it has to have a radical left there, because you can't find a perfect number or a whole number that multiplies to itself twice to get 8. It's got to be something like this. Usually we put this in the calculator to get a value like this. Before we get into simplifying, I wanted to show you another rule here. That rule is, so when the radicand is negative, what's the radicand again?
The inside number.
That's right, the radicand is the number that's found here. Could be a number like this, could be x to a power, it could be a whole expression. Whatever is under the radical is called the radicand. So sometimes this radical or this radicand can be seen as a negative. It's allowed sometimes, but other times it's not allowed, it's not defined. So let's start with a simple example here. Again, we look at this and the index is 2. So we said, what number multiplies by itself twice to get 9? That number is? Or what is the radical index
3.
of 9? Number is 3. But what do we have a negative here? Same expression, but with a negative. What number multiplies by itself to get negative 9? Or can you multiply negative by itself to get a negative?
No.
Can you multiply a number by itself and get a negative?
-3.
It is not -3. So whenever you multiply a number by itself, the result will always be positive. Okay, so when you multiply a number by itself, negative or negative, positive or positive, the result will always be positive. So it cannot be negative. So this is impossible here, at least in the group of real numbers. We say this is undefined. Okay, again, you can't find a number that multiplies by itself to get a negative. This is fine, but this is not okay. And this is the same thing for any even index here. If it's 4 or 5 or 6 or 8, if you have an even index, each 2 will multiply to a positive. The result must be
You have an index be negative.
The index cannot be negative, at least for now. With the radicals, we're only going to be dealing with positive indexes. So again, whenever you have a negative here, this should not be even. The reason is because, again, when you multiply any even numbers, any number an even number of times, the result must be positive. It cannot be negative.
Positive.
But what if we have an odd index here? What if we have this? 3 an index and we have a negative 8. Can we find a number that multiplies by itself 3 times to get negative 8?
-2.
-2.
Negative 2. You see how this is possible? Even though we have a negative, there is no problem here because this is odd. And you can check, you can multiply -2 by itself 3 times.
So the -9 was undefined because there's no number that multiply by itself gives -9.
So this one
Oh,
is defined, okay? You can double check it. You can say -2 by itself 3 times. You can say -2. So these two will turn into a positive. That's 4. This negative will stay here. So if this is odd, there's always going to be one negative remaining and it will make the result negative, which is fine because we can get that number here. But with these, if this is even, the result always going to be positive. Each 2 will multiply into, for example, -2. In this case, actually it's undefined. So each 2 numbers will always multiply to positive. Each 2, so the result will always be positive if we break it down. But with an odd index, it is possible to have a negative. So bottom line, if you see a negative here, then check the index right away. If the index is even, meaning 2 or 4 or 6 or 8, if this is even, then right away, you don't even have to try to simplify or find the answer or do anything. Don't waste time doing any of this. Just say it's undefined. It's not a real number. It could be a complex number, but it's not a real number. It's not in the group of real numbers that we talked about in the beginning of the semester. However, if you see a negative here and the index is odd, then it's fine. You can have that. What about this number? Is it defined or not? First, decide if it's defined. If it's defined, then you find the answer. If it's not defined, don't waste the time. Just say
It's
undefined.
-3.
Fine.
-3.
Right, it's -3. So
Yeah, it's negative.
it is defined because even though we have a negative, this is odd, so this is fine. For the next 2, I just want you to tell me whether it's defined or not. I don't need the answer. I don't need the value. I just need to know whether it's defined or not. Let's say we have 8 here, -144.
Not defined.
Not defined. That's why we have a negative. This is odd. Again, you can't multiply a number by itself 8 times to get a negative, so this is undefined. That's it.
Is it every time you get an odd number, or how do you know?
If the index is odd, you can have a negative. Okay. Just
You can. Okay.
Here's an example. Let's say you have 11 here and you have -2, I don't know, 8, 4. I don't need the answer. I don't need the value, just whether it's defined or not. Is this defined?
Yes.
That's right. It is defined because we have a negative. This is odd. So that's fine. So we say it's defined. And if it's something that makes sense like this, from these that, at least from these that we learned, you can do this without a calculator. If it's something that you can't possibly do with a calculator or without a calculator, then if you actually need the value, you can plug this in the calculator to find the value. Calculators have some buttons like this, where you can put the index, write the radicand or something like that, but we're not going to be using calculator in this class. We're going to try to do everything manually with the formulas. If it's something like this, we leave it like that, so we don't have to simplify. So let's write a couple of things here. So for any radical like this and x, let's assume x here is positive. Okay, so assume here is x is positive. So if the index if the index n is even. Finish the sentence. What do you say about x? X can't be what? If the index is even, like here, x can't be what sign?
Negative.
That's right, it can't be negative. Again, with this example. The other case is if index n is odd, x, what's the rest of the sentence here? X can be?
Negative.
That's right, can be negative. That's basically the thing here. So even x can't be negative. Odd x can't be negative according to these two. These are a few problems. So this stuff you need to know before you try to simplify something. You will not tell you in the question or the problem that this is undefined or this or that. You have to figure it out yourself to save yourself time. And again, for example, here, you don't have to look for a number. We know for a fact this not a defined value, just say undefined. You can't use it in the calculation. You can't do anything with it. If you see this, you know it's defined. You know that you can find it either like this if it's easy, or you can plug this in the calculator to get the exact value. So these are important along with what we talked about before. Okay, so most of the time, we'll give you something convenient like this that you can find. Just read your radical in this form, try to find a number. If not, again, we can either use a calculator if we really have to find a value, or we can leave the expression as it is. Back to this again. So we said radical 9, we know for a fact is 3. 3 times 3 is 9. Because the index it is invisible, it's 2. Same thing here, index is 2. But we can't find a whole or an integer number that multiplies to 8. We can either get, if we really need a value, specific value, we can use a calculator to get a decimal. If not, most of the time would be an irrational number, as we talked about in the beginning of the class. Irrational number, for example, some number like this with a non-ending, non-repeating decimal, something like this. Or if you're lucky, you get something like this, the value is an integer. So now, again, we do not like to write decimals, but we're going to try to simplify this as much as possible. Let's get back to this one and see how to break it down a little bit, as close as possible, but not exactly as a whole number like this. So that's what we're going to call simplifying radicals. So the second part.
Professor, can you bring the page back a little bit, just a little bit?
Like this.
Thank you.
Mm-hmm. So simplifying. Again, we are lucky when we have something like this. We can say 3, because 3 to the second, the invisible index is 9. But if we have 8, the index again is invisible 2. We can't find a number unless it's a decimal. So what we're going to try to do is we're going to try to break this down into 2 radicals. 2 numbers are multiplied to 8, and hopefully one of those radicals has a perfect, one of those has a perfect root, or a perfect number like this. By that I mean a whole number or an integer. Think about 2 numbers are multiplied to 8, and one of which has a perfect root.
4 and 2.
That's right.
2.
2, 4 and 2, radical 4 times radical 2. Well, of course, now radical 4, or the square root of 4 is.
Do both numbers have to have a radical?
That's right, yeah, because we
Okay.
brought down this radical. Radical 4 is
2.
2, and this 2 here stays under the radical. And that's it. That's as simple as you can get with the radical. As you can see, the number here got smaller.
You always have to keep one number in radical?
If it doesn't have a perfect radical, perfect root like this, there's always going to be a number that stays inside. Okay?
Can you repeat that? I didn't understand. You say that if it doesn't have a perfect.
Yeah, so not every radical is perfect. So sometimes we have to break it down like this. Unlike this, there's no radical left, but sometimes a radical stays in the expression.
Oh, okay, because like the 8 has a cube radical, but not a square radical. That's perfect, right?
Yeah, exactly.
Okay.
This is a square, not a cube. And basically, that's the simple form of this. As long as you can't break this down anymore, so that's done. We can also say we have a cube. Let's say we have 16. Okay, do we know, or can we find a whole number that multiplies by itself 3 times 16? Or, so if you can't figure out that number, these is basically the cubes that are perfect are 1, 8, 27, 64, and 25, at least for the first few numbers here. So if you don't have one of these, then you're going to try to make one of these from the number you have. Just like with the 8. So if you have a 9, you're lucky. 9, we know he has a perfect root. But if you don't have one of these in the radical, so you're going to try to break your number. For example, we had the 8 here. Try to break the 8 into 2 numbers from here. The numbers were 2 and 4. We used here 2, 4, and 2. So now we have cube of 16. We're not sure what that is. We know what the cube of 1 is, of 8, of 27, of 64, of 125. So we're going to need to break this down into some known cube and another number. So what can we turn 16 into?
8 and
Radical 8 and radical 2.
That's right, radical 8 and radical 2. Both are cubed. So if the index is different than 2, we have to write it. You don't need to write it if it's 2, if it's the square root, but with the cubes or any other ones, we must write that cube here.
Even though the product of those things are not cubed.
They are cubed.
Oh, because you have to find a number, two
So
numbers
cube,
that give.
the cube always stays there. The cube always gotta be there.
But why are they cubed? Because you're finding something like you're finding 2 numbers that multiply to 16 that have roots.
Yes,
Okay.
one of these has to have a perfect root. So now, what is the cube of 8?
2.
That's right. So this gotta be 2. And this stays the same. So it's 3 and 2. So you can see we can't break it down anymore. And this is a decimal number. The cube of 2 is a decimal number. So we better leave it like this. Unless, again, we're looking for a precise value with the decimal, then we can multiply 2 by this in the calculator.
Teacher, I don't think I'm getting it because I don't understand how this is simplifying the 16.
Well, if you just listen for a couple of minutes, I will explain it, okay? Let me just finish the explanation and then ask you a question.
Okay.
Let me
Only
give,
one of those is gonna turn into the perfect root.
hold on, let me give you another example and you guys will get it better. Let's say you have, say we have 27 here, and it's a square root. Do we know the square root of 27 to be a whole number? Do we know, does this have a perfect radical or root?
No.
No, so that's when you start thinking about breaking this down into 2 numbers. Those numbers, one of them should have a perfect root. So what number?
9 and 3.
3.
9 and 3.
9 and 3.
9 and 3. Now, which one simplifies?
The 9.
9.
9 turned into 3. This stays the same. That's the whole concept. If you can't find the root of the radical, think about breaking it down into something. Let me give you another one before you speak. Let me give you another one. Let's say you have maybe 50. Again, it's a square root. Do we know the square root of 50?
No.
No. So now we need to turn this 50 into two numbers two numbers or two radicals. One of the radicals must have a perfect root. There are multiple numbers that multiply to 50. You can get 50 by multiplying
25 and 2.
25 and 2. You can also get 50 by multiplying
5 and
5
10.
times 10.
10 and 5, that's right. But which one is convenient to use to get a...
The first one.
5 and a 2.
That's right. So this is not going to help, even if we use two of these. We don't know the radical of 10. We don't know the radical of 5. We're going to need a calculator for that. But this seems convenient. So we're going to rather use that. Okay, so now this turns into a 5 and a 2. Okay, so you have to choose the right combination. Break the number down, figure out which one is the right one to use. I believe that's what the confusion that you guys had, right?
Yeah, I guess I didn't understand. I didn't understand it was like you had to multiply two numbers that get the radical of the 50, and then one of them has to be perfect.
Right. So the
Okay.
we get another example here. So we know that radical 25 is nice, it's 5. But what if you have 24? It's very close, but it's not exactly 5. That's when you start thinking again about two numbers that multiply 24. It might be multiple combinations, but you have to choose the perfect one. So give me all the combinations that multiply to 24.
6 times 4.
6 and
4.
6 and 4, then
12 and 2.
12 and 2, then
3 times 8.
that's right. So all these multiply 24, but only one of them is going to be helpful in simplifying this, which one has will give you a perfect root,
6
or at
times,
least one of the numbers.
8 and 3.
6 times 4.
6 and 4. So obviously, so you can get the square root of this one. So invisible 2 here, square root. None of these has a square. None of these has a square. You'll have to break it down more. So this seems to be the best one to use. So we're going to use radical 4 first. So again, radical 4 is 2 and 6. And not every time you break this number down, you get a perfect radical. So we have 6 here. There's no way to simplify radical 6. The only two numbers are multiplied to, or two combinations are 6 and 1, which is not helpful. And then we have 3 and 2. Both not going to help simplifying this. So this basically stays the same. Okay, so you need to do a little bit of breaking down the numbers here in order to figure out your best combination. What if for some reason, if you get, I know this doesn't multiply to 24. Let's say for some reason there are other numbers that multiply 24. One of them, for example, is 9 and some number X here, whatever. Just an example, just hypothetical. Which one would you choose? Would you choose the one with the 4 or the one with the 9 to simplify?
I would choose one with the 4 because we're dealing with square roots, not cube roots.
You would actually find the largest number.
Oh yeah.
The one with the largest perfect root. In this case, again, this is just a hypothetical situation. If you have two possible combinations of both give you a root, you go with the one with the higher number. So in this case, we would take the 9. I know this doesn't apply to 24, but if you have two roots or more, take the one that gives you the highest number, the highest perfect root here. Okay, so that's basically how you simplify radicals, even if they don't have a perfect root. And as always, before you simplify anything, make sure it's defined. If it's not defined, you don't need to waste time finding anything. Let's see another example here. Let's say 48, for example. And again, by default, the index is 2. So how would you break the 48 down? What is the best combination to use?
16 and 3.
Okay, that's one of the combinations. Any other possible combinations? Any other numbers that multiply to 48?
6 and 8, 12 and 4.
24 times 2.
12 and 4. This is a very good example. Anything else?
24 times 2.
24 times 2. All these multiply 24, but which one is the best to use to simplify? With the highest, basically.
16.
16 times 3.
16.
Yeah.
That's right. This one has 16. This one also has a perfect root of 4, which is 2, but we would take the highest one. And that would be radical 16 times radical 3, which is basically 4 radical 3. Basically, you try to get this number inside as small as possible to the point that you can't break it down anymore.
Would you ever make us reverse it from a simplification to get to the 48?
When we're going to do that when we get to the multiplication of radicals and addition and subtraction, yes,
Oh,
we
okay,
have to
perfect.
multiply this. Okay, so for this one here again, you see, if you use this combination instead, this will turn into a 2 here, but this number is not as small as 3. You still have to break it down again. So basically the goal is to try to get this number as small as possible so it can't be broken down anymore. Once you do that, so this is the simplest you could get. If you use this form, it will be 2 radical 12. Okay, this turns into a 2, you'll have radical inside, but this it's not as good as this one. You will still have to break this down again. It will be radical 2, radical 4, radical 3. Still have to break the radical 12 down again. It will be 2 times 2, which is 4 times radical 3, and you get back to this. So it just adds extra steps. It's still going to be the same answer, but you have to do that again. So it's better to find the best combination, so you don't have to waste time simplifying again. What else? There is another. So this applies again. Be careful with the exponent before you simplify. Let's say, what about here? This again, see how we did this here with index 2, but now we're going to do it, but with a different index. It's completely different. So again, radical or the cube of 24 is not one of these, the common ones. It's close to 27, but it's not exactly 27. So we're going to try to break that down and get a couple of these here.
8 and 3.
Was that simplification only for cubes? Or cubes and squares, right? Okay.
It's for any index,
Oh, any index, okay.
Okay, so now we don't know the cube of 24. We only know the first few, 1, 3, 27, 64, 125. So now we're going to try to break this down. So what is the best combination to use here?
8 and 3.
8 and 3. So you might be thinking about 12 and
12 and, yeah, 2.
2, 6 and 4.
6 and 4.
Which one of these has a cube?
12 and 2.
A cube, not
3.
square.
8 and 3.
This one. Okay.
8 and
one. And this one. Again, we're talking about this one. We're talking about index 3, not square. So not this, but actually this. And you have to write your index whenever it's different than 2, it must be written. Of course, this is the cube of 8.
2.
2, and this stays here. And that's as simple as you can get. Again, be careful with this. See how they're completely different. This is square root or the index 2, and this is the cubic root or index 3. Okay, so again, it helps to know at least these first 10 squares with the square root, and first at least these 5 here with the cubic root. And any other cube basically works, any other index works the exact same way.
I have a question.
Mhm.
Can you explain cube one more time? I don't know, up where you were just now,
Mhm.
upwards. I understand root and how you got
Here,
this.
so from this line here to here, we cubed the numbers. It means we'll raise them to the third power. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27. So from here to here, we cube. To go back, we get the cubic root. This is basically the whole concept of radicals, as I said earlier here. We just go back between exponential expressions and radical expressions. So these numbers, when cubed, you get this. But to go back to the root, we do the cubic root. Same thing with the squares. So 1, 2, 3 to 10. When you square them, you get these numbers. But for, to go back, you use the square root. Here we square. The opposite of the square is the square root. And we go back from 100 to 10. Square root of 81 is 9, and so on. Okay, so here's another form or another expression, or rather another formula. Let's see. So you have this, you have some power here, some index. So we can turn any radical into an exponential expression. So this is radical. We can go back and forth between radicals and exponential forms. It's very simple. What you do is you take the base. You take this power divided by the index. Okay, any radical, just take the base here, take its power divided by n. Not the other way, divide this by this. So this is radical form, this is exponent or exponential form. Example, let's say you have 2 to the power, I don't know, 8 or 6 by 2. Let me actually make the index a little different. Okay, this is radical form. May look like a complex expression, 2 to the 6 and radical index 3. But if you use this formula, we can turn this into an exponent form, and then we can probably simplify it easily. So what is this equal to if we use this same
2 to the 6/3.
Yeah.
all right, 2, 6 divided by 3, which is 2 to a power,
2 to the 3rd.
which is,
2 to the 2nd. Yeah, 2 to the 3rd.
which is, I mean, to the
2
second.
to the 2nd, yeah.
To the second.
4.
Choose 4. See, you may have looked at this and thought it was complex, so we need to calculate. But yes, actually, you can do this quickly here. You see, it's just 4. Just divide this by this. Even if you have a variable, assuming this variable is positive. I'm going to talk about this. Assuming it's positive. The reason why I say it's positive is because earlier we said.
I don't know what it is, if it might be undefined.
Exactly. So this number here, especially if the index is even, it can't be negative. That's why sometimes you will see this x has to be greater than 0. So to avoid the case where it's undefined, so we say, we know for a fact that this is positive, so we don't care about the index, whether it's odd or even. So let's assume x is positive here. That means it will not be undefined. So it will be good whether this is odd or even. So again, let's say you have, I don't know, 15 and 5 here. This looks complex, right? But if we use this transformation here, we can turn it into
X to the 15 over 5.
That's right, 15 by 5. Again, always divide this way, not the other way. So 15 by 5, which is 3. So this is much, much simpler. These are the same expressions, but this one looks complex. This one just x to the 3rd, whatever that x is. Again, assuming it's greater than 0, so it's defined.
Professor.
Yeah.
So inside we leave the same number. I mean,
Yeah, take
x.
And
that base stays the same, yeah.
Okay.
Whatever the base is, just take the power of that base divided by n index. And something can be very complex, but you can do it in 2 seconds. Let's say, give you another one. Let's say 7 and 200 divided by 100. So this is something that you might think is very complex, and with the calculator, it will take you a long, probably, just a few seconds. But you can actually do this in 2 or 3 seconds without a calculator.
We have to divide, yeah?
Yeah. Can someone give me the final answer in one shot here? A couple of seconds.
49.
7
49.
to the 2nd power.
That's right.
49.
Just 49. Okay, because you know, divide this, you get 2, and 200 by 100 is 7 to the second, it's 49. Okay, again, you can do it faster than a calculator. Imagine if you had to put this in a calculator, it would take you at least probably 10 to 15 seconds, but with the rule here, you could do it in 2 seconds. Okay, that's why I said we're gonna try to do everything manually with the formulas, with knowing the basics and the foundation and the rules without actually having to use a calculator. The calculator is not always helpful. If you don't know these rules, you're just gonna waste time using a calculator, especially if something is undefined. You're gonna try to punch something in the calculator that does not exist, punching numbers that probably are undefined like this. But if you know your rules, this takes you less than a second to answer, as opposed to, I don't know, spending a couple of minutes trying to find something that's undefined. And you'll get some error messages in the calculator when you try to do something like this. Okay, speaking of this rule here, so again, this is one of the very important ones. So this stuff here, along with these rules, and what else? Of course, know your, at least these basics here. And here we can turn the whole equation from exponential to radical. Okay, that in addition to this one. So let's try to do, say we have 3, I'm just gonna put some random powers here. So we want to multiply these, right? But again, we're not actually multiplying the radicals yet, but we're going to try to use the exponential forms. So we're going to try to make both of these, turn them into exponent forms, and then apply the rules of exponents that we know to them. Okay, so let's use this to turn both of these radicals into some exponent expression. So what do you get from the first one? We want to turn this into an exponential expression. It will be 3 to
3 to the 2/5.
right, to the 5th times this one here.
3 to the 1/5.
That's right. So the power of 3 here is 1, indivisible 1. So if we use this formula, we're going to divide 1 by 5, it will be 3 1/5. And if you recall the rules of exponents, what is this equal to?
9 to the,
No, here, for this one.
oh, A plus B.
A plus B.
That's right. And also if you have A to the power B, this will be?
Multiplication.
That's right. So all the rules that we know of exponents, they also apply to, I mean, if you switch your radicals first to exponents, and then you apply all the rules. So if you're multiplying this, again, it looks confusing here, but it looks easier when we turn them into radicals, into exponents. And then from here, we can use the first rule for this one. We're just going to add the 2. And this is basically 3 to the power 3 over 5. Okay, so we just added these two into that. And let's try to go back again. Let's try to turn this back into a radical. So what would this be as a radical, like this?
Radical 3.
Okay.
3 to the 3rd root
Right, 3 to the 5th.
To the 3rd and the index.
5th.
To the 5th.
That's right, 5th. Okay, so you see how we did this. First, we kind of changed both into exponents because exponents, we know their rules, and we finally got this. These are some tricks you can use when we multiply radicals. Again, after we can't multiply right away, and when we don't have perfect radicals, we can resort to this.
Es que el Zoom quita un montón de.
We're gonna see more rules of multiplication. Let's see another one here.
Before you go to the other one, how does I mean, I know why the end result is index 5 through to the third, based on how everything is set up at the end, but how did we get all the way down here? How would that be an answer? Like that would be the answer, or if that's only if they want us to revert back to radical form? The very last thing.
This would be the answer. I mean, depending on the question.
Okay.
But these are pretty much the same number. Maybe it would ask you to revert back to this or something, but basically the same number. You can switch back and forth.
Okay, I see. Okay.
Let's see another problem here. Let's say you have this 3, maybe 2 here, and to another power, let's say, whatever that power might be, 4, for example, here. The same thing here, we're going to try to turn this into an exponent. We have another exponent here, and then we're going to try to use one of these. So what is this as an exponent again, the inside?
4 to the 3.
4 to the power?
4 to the power 2 seconds, 3.
3 by 2, that's right. And all to the power?
4.
4 here. And which rule of these do we use for that?
Multiplication.
That's right, will be this times this, 3.
12 to the second.
All right, times 4, which will be 4 to the power. 3 times 4 is 12, by 2 is 6. And that's a much easier number. And you can find the value of this if you want to. It's going to be a large number, 4 times 4 times 4, 6 times, but this is good enough.
Teacher, for the one above that one, do you want us to write it as 3 to 3
Well,
fifths?
the question
or-
will tell you. The question will specify.
Oh, okay.
So about either one, you both correct answers. So this is one way, again, remember, all the radicals can be turned into exponents. And once you have exponents, all the rules we did with the exponents apply to them. This is one way to multiply radicals and simplify them. We're going to see more operations. We're going to see more multiplications, additions, subtractions in the next class. Pretty much, I believe that we covered everything. Guys, have any questions, everybody? Any questions about any of this?
No, not so far.
So this is your introduction to radicals. It's very important that you know these rules very well. There's no room here for guessing or for, I don't know. You have to know your rules here. Once you know them, you will make your math a lot easier and faster. But like I said, you can do this stuff within seconds. If you don't know rules, again, it's gonna be a little rough. Let's see. The last part here is, let's see. This is good enough, I believe. We're gonna do more simplifying next time. More multiplying. Yeah, we're gonna do more operations. This is good enough for today. I don't want to give you too much information for now. All right, so that should be enough for today.
No examples, like self stuff?
Who said that?
Let me give you a couple. Let me give you a couple of practice. Yeah, let me write. I think we have a lot of time. Yes, I'll give you a few problems here.
The person that said that.
It's better, Jermaine. It's better.
Teacher, can you take attendance though?
We'll take
Will
it.
we practice?
I'll take in a few minutes. Let me write first this practice. I'll let you work on it.
Who the person that said
I love you too.
Okay, so give you something like this. Okay, so simplify these radicals. And okay, that's your practice. Again, most of these should take you seconds. Okay, take a few minutes to work on this while I take the attendance. Are you guys finished? What is the answer here for the first one?
12.
Right,
It will be 12.
that's right. The index indivisible by default is 2. What about this?
6
Index
radical
Was it
2.
2?
radical 2.
So that's right. That is 6 and 2. That's 6 radical 2. And here,
2 radical 4.
8 times radical 4, right? The index is 3, so don't confuse that with the square root. Whereas
got-
Radical 4 cubed.
I broke it down more. I have 4, excuse me, I have 2 index 3 radical 2.
So what is the cube, highest cube we can get from here? So we have either 8, 27, or 64. So this is the highest one we can get, right? 8 times 4 is 32. And again, the index is 3.
And radical 4.
So this is 2, and the radical 4 is basically just that. It's not 2, it's not a square root, it's a cube, it stays like that.
I used 16 and 2. I used the wrong one.
16 and 2, we don't know the cube of 16, that's the problem.
Yeah, I know. That's why I was saying I used the wrong one.
This one here, what is this equal to?
-5.
Yeah.
This one first.
Sorry.
The number
2.
the number that you multiply by itself 5 times to get 32
Two.
is 2.
2.
Okay, the number that multiplies by itself
Mhm.
5 times to get 32.
Yeah.
Number is 2. 2 to the 5th. If you want to check, to the 5th is 32. And here,
It will be
-5.
-5.
5.
minus 5. What about this equals?
Undefined.
Exactly. You have a negative.
Undefined. Mhm.
That's right. It's undefined. No need to
It's
waste
undef-
time. Undefined. And is this defined or not?
Undefined.
Why
No,
is
that's
it?
fine.
No,
So,
it's 9, no?
so this is this a positive or a negative number?
That's gonna turn out to be +9.
Exactly, because the power
Positive
is
9,
even.
yeah.
Power is even. So each
Mhm.
two negative threes, each two gonna turn into positive. So this is actually a positive number. So this is defined. So we need to find it.
Mhm.
And what is this equal to if we use the rule we talked about earlier?
I got 3 to the 4th power.
It's gonna be 3 to the 4th power. That's right. Forget to mention when you have a situation like this. So it's gonna be the absolute value of this. Like we said, this can't be negative. So the absolute value of this. And we divide this by this as we did earlier with the rule. So 12 by 6. So it'll be 3 to the power
2.
4. I mean 2, which is
Mhm.
9.
It's positive 9, yeah.
Okay, just make sure you take the absolute value of this when you have a situation like this. This is a positive number, okay? That's why we need to take the opposite of this. And for this, it would be 5 to the power
2.
4 over 2, that's right, which is 2. You just add in the 2. And for this one, it's going to be 3 to what power?
4.
We cancel these, that's right, 2 times 2 would be 4.
4.
Which is
81.
81.
As you can see here, we did all this in a couple of minutes without a calculator. Thanks to the rules. So if you know your rules, you can save a lot of time and trouble. And that's pretty much it for today. Any other questions, everybody?